Hello, welcome back. So in the previous example, in the previous part, I was explaining the connection design. So in that we have done bolted connection when lacing bar are not overlap to each other. So now in the B part, I will solve the bolted connection when lacing bars are overlap to each other. So I have shown you in the previous part that if the lacing bar are overlap to each other, in that case the bolt will be in the double shear. So in that case, we are going to find out the strength of bolt in double shear, and simply we will multiply this with the 2 because in this case bolt is in the double shear, which means the strength of bolt in shear is increased. So strength of bolt in double shear will be 74.294. Similarly, if we find out the strength of bolt in bearing, again we have to put the kb value. So I am assuming here kb value as 0.49. You have to actually calculate it, but I have shown you the process how do we find out the kb value. So here I am directly assuming the value of kb as 0.49 because generally kb value is around zero point 0.5. So putting the value, we can calculate here which is 88.167. So here again you can see this value is the lower one, so we can adopt this we can take this as the strength of bolt. So strength of bolt is 74 kilonewton approximately. And while you know that the number of bolts required formula will be force in the lacing bar divided by the strength of the bolt. So this time what we have done is, this time we have calculated the resultant force. I hope you understand. Earlier I told you that if the lacing bar are overlap to each other, in that case what we do is we find out the resultant force. So I hope you remember this. So this is how we are actually finding the resultant force, and resultant force we are putting there, which is 25 by 37. So here again you can see the number of bolts required will be 0.7, which is again less than 1. So we are providing one bolt at each end. So I have made the diagram. So you can see the diagram, it will look like this. So these are the lacing bar, and at each end we are providing the bolt. This is the batten plate. So we are yet to design batten connections that we will design in the next lecture. So we will see that at that time. So till now we have designed these two sections and then the lacing bars. So that is the diagram generally we will make when we solve the problem. So this is the case when bolted connections is to be used. Now in the next part, not in the next part, I will be explaining this in this part only. Now we will see how do we design the welded connection. In the flange, in the welded connection, like if these are the components which we have to connect, so lacing bar will be like this. So in that case, we can connect with the welding. We have available this part which we can connect with the welding. So ultimately we have to find out first what will be the length required to connect this lacing bar. So in the lacing bar we already know that the force in the lacing bar will be 17.67. I think this is the force in the lacing bar. So for supporting this much force, how much length of weld will be required, that we have to find out. So that is actually the basis of welded connection. So in the welded connection, we are going to find out that length. But to find out the length of weld, now if you remember the formula that we use in welded connection, uh, based on that we will find out various criteria. So first thing that we are going to decide, I'm deciding here that we are going to use fillet weld. So there you can see these are the fillet weld that we are going to use. So if I cut the cross section, it will look like this. So this will be the fillet weld that we are going to provide. So this section something look like this. So this is the lacing bar and this one is the flange of this part. Okay, so now in the fillet weld we are going to find out the size of weld, this one, which is S, and also the throat thickness. So throat thickness, which is TE, zero point 0.7 times of S. So S depends. So first of all, we have to find out the range of size of weld, minimum and maximum range. So flange thickness of ISMC is 13.6. It is as per the as per the steel table. And minimum size of weld for 13.6 mm thick member, as to find out the minimum size of weld, generally we see the thicker plate. So in this case, the uh, size of lacing bar is, the thickness of lacing bar is 12 mm, and thickness of this flange, this one, this is actually 13.6 mm. So the thicker plate is this one. So based on this, we are going to see the minimum size of weld. So for 13.6, minimum size of weld will be 5. So as per table 21, minimum size of weld will be 5 mm. So what we are going to do is we will adopt this size, and based on this size we will find out the length of weld. But that length of weld, we will find out strength of weld per unit length. For a unit length, what will be the strength of weld when we use this size of weld? So I hope you remember the strength formula for welding we generally use is L into TE into FU upon under root 3 into gamma MB. So this is the formula that we generally use. So here we are calculating for the unit length. So here if L is equals to, if I put L is equals to 1 mm, then throat thickness will be 0.7 times of size of weld, and FU value we already know it will be 410. Gamma MB, well, also we will assume that it will be field welding. So in case of field welding, the gamma MB value will be 1.5. Okay, so based on that, now I am showing the formula. So there, this is the throat thickness, and L value, length of weld, I am taking here as 1 mm. So for 1 mm thickness, what will be the strength of weld that we are going to find out? 410 is the FU value, gamma MB under root 3. So by solving it, we say that 552.33 Newton per mm, which means 1 mm length of weld will be having this much strength. Now we are going to find out length of weld because we already have the force. So length of weld will be calculated as, force in lacing bar upon strength of weld per unit or per mm length. So if this is the same value I have put here, so force in the lacing bar is 17670. So putting the value, we get the required length, which is 32 mm. So which means only 32 mm length is required to support this much load. Which means if we provide more than this, then we will be on the conservative side. So this 32 mm, beside this, we have to add the end returns. So end returns generally are 2 times of 2s, because if this is the bar, then if we provide welding on this side and on this side, then this side will be the end returns and this side will be the end returns. So there will be 2 end returns. So 2 multiplied by 2s. So end returns specification I have already mentioned in the welded connection. So I hope you remember that. So based on that, the length which we can provide here is 52 mm. So now what I am going to do is I will provide 100 mm length. By providing more length, I will be on the safer side. So I'm providing 100 mm length. It is up to you whether you provide 60 mm or 70 mm, but ultimately we have to provide sufficient length of weld so that the force in the lacing bar can be supported easily, efficiently. So now after that we will make the diagram. So in the diagram you can see uh, I have provided the length, I mean the welding on both sides, on all around, on all three sides in the plan. You can see. So this is how we provide. So lacing bar, I have identified this as 50 ISF. 50 is the width and 12 is the thickness. ISMC 300. So this is how we make the uh, diagram. So this concludes the solution of this lacing numerical, this problem. So in the next lecture, we are going to discuss about the batten system. So till now in this part, we have discussed about the lacing system. In the next part, we are going to discuss the batten system. Thank you.